I'd like to speak to you about irrational numbers, specifically their existence, or the proof of their existence. Now, among the fractions, or numbers which are not whole numbers or integers, there are decimal numbers, which it may not be immediately obvious are rational, but for example, the number 3.14 could be written as 314 over 100. So it is in fact rational. And in a similar way, any terminating decimal, that is a decimal number with finitely many decimal places, can be expressed as the quotient of two integers. And indeed, even a decimal which has infinitely many places, but which repeat according to a prescribed pattern, can be expressed as a rational or a fraction. So, for example, 1/3 is 0.333 repeating, and 1/7 is 0.142857, 142857, and so forth. So any such repeating decimal or decimal number which has a sequence of digits repeating according to a cyclic pattern can in fact be expressed as a quotient of integers. And any rational number, fraction, quotient of integers, can be expressed either as a terminating decimal or as infinite decimal with a repeating pattern. Now, the square root of 2, according to a famous result, is in fact not expressible as a quotient of whole numbers. And this result is often attributed to Hippasus, the Greek mathematician, who was interested in measuring the hypotenuse of a triangle, two of whose sides measured a length of 1. And the proof, which occurs in Euclid's Elements, proceeds as follows. Suppose that the square root of 2 were a rational number. Then we could simply write root 2 as a over b, where a and b are integers, and in fact whole numbers, but we could make both a and b positive integers, which means that, and not only that, but we could reduce them to lowest terms so that their greatest common divisor is 1. And as a consequence, we would have the equation square root of 2 equals a over b. Now, if we squared both sides, we would find that the 2 is equal to a squared over b squared. And by either cross-multiplying or multiplying both sides of the equation by b squared, we would find that 2b squared is equal to a squared. Now, from this equation 1, notice that 2b squared is clearly even, or divisible by 2, and a squared being equal to it must also be even, or divisible by 2. But in order for a squared to be even, a itself, which is a whole number, must in fact be even, because if it were odd, a squared would also be odd. The square of an odd number is odd. So in fact, a is divisible by 2, and we could therefore write a as 2c. And by substituting 2c for a into our original equation, we'd find that 2b squared is equal to the square of 2c, which is 4c squared. Dividing both sides by 2, we would obtain b squared equals 2c squared. And then simply repeating this argument that we made above, we find that because 2c squared is even, b squared, which is its equal, is also even, and therefore b is also even. So we have that 2 is a factor of both a now and b, which is contrary to our original assumption that the a and b are relatively prime. And so the only logical conclusion to reach is that it was in fact not possible initially to write the square root of 2 as the quotient of two natural numbers. And so we have a new number, new type of number, an irrational, which is considered a real number, but is not rational. Now we can write the decimal expansion of this 1.414 and so forth with an infinite string of digits with no repetition, or rather, at least no cyclic pattern. And then we might ask, well, what's the significance of this number? For example, if it's not really possible to express it as a terminating decimal or as a fraction, then does it really exist? Well, certainly we could say that if we were to draw a square with an area of 2 meters, then the side length of the square, 2 square meters, then the side length of the square would be the square root of 2. And another way to approach it would be to draw a triangle with a side length of 1 meter, a right triangle with the two sides adjacent to the right angle equal to 1 meter in length, and then the hypotenuse would have to be, according to the Pythagorean theorem, equal to the square root of 2. So the square root of 2 is genuinely a real number, but just not rational.